Okay, so second class about competition, modern competition theory. So just to review what we had yesterday. Yesterday we talked about intraspecific competition, and our point was intraspecific competition for resources. Instead of writing directly the logistic equation, we should write an equation with the resource and the consumer and the resource, and then just see what happens. Right? So what happens is, well, we had already written such an equation when you had the logistic growth of the resource. We know there would be oscillations in going to a stable fixed state. But then we also showed that in a certain limit, when the resource has a turnover time which is much smaller than the consumer, we can describe in this limit the logistic equation is a good approximation. Okay, so this gives a better status to the logistic equation. Well, then when we consider the abiotic resources, or biotic but managed by experiments or something, it turned out that in the same limit the logistic equation did not emerge, and a different equation, but this equation contains some more parameters, which never mind now. And so this, sorry. And then inspecting this numerically, it turned out that the solutions are very close to one another. Okay, so within the possibilities of measurements in fields and so on, it's effectively a very small effect from the difference from the logistic equation. So you could say that's not at a very fundamental level you didn't find the logistic equation, but well, it's something that's very close to it. Okay? So this this is important from a theoretical point of view, because we go on using carrying capacities all the time. Okay? So the concept of carrying capacity emerged from consumer resource relations. So this is better, say, theoretical thing. Okay. So now we want to go to much more the modern competition theory. We will start again, and we will do this with a little bit simplified dynamics. So instead of supposing logistic equation for the resource, which is obviously nonlinear and so on, I will suppose that there is a new term which is kind of abiotic-like, okay, which is it's called burst, a resource term, growth of the resource in a chemostat. Okay? So this is not fundamental. This is just, I could change everything for logistic growth. Okay? But it's better to do simple things. And so you will see what we will consider. So let's come back first to one consumer, one resource. Okay? And well, the objective today will obviously be that we want to study two consumers with one resource and so on. Okay? So one consumer, one resource. The consumer is N of T, and the resource is given by R of T. And we will write this in the usual way. It's R times. So the resource is fundamental in this case. It's a specialist. and there's a depth term. Okay, so this is very simple, like logs of Voltaire. Okay, but we will do something different for the resource. So R is I'm using R where I used to use alpha before. Okay, but you get acquainted. You get used to the changes of the names of the parameters. Parameter names are completely arbitrary. Okay. And then I have I will have a depletion, which is R times a small r times some gamma, another constant, times R times N, and that's it. Okay? So, and a term which I will call I times S minus R. So what is this? So this is what we already know. This is also what we already know. I'm just making a small difference that I'm putting gamma here, which is, and usually I put the efficiency here. Okay? That I can rename R times gamma as alpha and then say this is find the efficiency here. Okay, so this is, it's just what we already had. And here I'm putting a new term, which is for a managed resource. Okay? So what does this term mean? So there's two parameters, S, which is a constant, and A. Okay? So if you, okay, now if R is bigger than S, then this term is negative. It creates a tendency to decrease the population of the resource. Whereas if R is smaller than S, this term is positive and there's an increase of the population. Therefore, this is a term that has the tendency to put the population at level S. Okay? So you see, that's a simpler way to have the population of the resource normally going to some constant value instead of using the logistic equation. And again, that's only, this is not an essential point. I could do with the logistic equation, but the algebra is not complicated, but there are lots of calculations with, and this one is simpler. Okay, so usually we will write this actually a little bit differently. So our question would, what? The mic, here's one mic.
Morning. Are the two R's on the two equations, the small r, the same letter?
Yeah.
Because you wrote differently.
Yeah,
I was kind of worried.
That's a different graphical representation. Okay. It's the same R. Okay. So, okay, are you okay with this equation? That's the basic consumer research equation with a linear functional response, all in type 1.
I just didn't understand very well why the first term is negative in the resource equation.
Because the consumer N is consuming the resource, therefore it tends to put the resource to lower levels. The consumer here increases due to the consumption of the resource, and the resource decreases due to the consumption of the resource. Okay, it's the same Voltaire story. Okay, Actually, this is kind of lockable term with some different element here. Okay? So now, this is easy to look for fixed points, which are the fixed points dn dt equal to 0 and dr dt equal to 0. And our life is easy. This here, I can factor out the n, and therefore r at fixed point, let me put r star, is equal to m over r. Okay? And this one, I cannot factor out anything actually, but I can put the r here, so I can factor. Okay, dr dt equal to 0 will mean that r times gamma times r times n minus a times s minus r is equal to 0, which allows me, and at fixed point, I put the star to say I'm at the fixed point. So n star will be a times s minus r star minus m over r divided by r gamma s minus m over r. Okay? This is correct, I think so. Let me see. No, maybe. Yeah. Or in other words, I mean, it's nicer to write this like s minus r star divided by r gamma r star. Okay? So these are the fixed points, and they represent an equilibrium between the resource and the consumer. Okay? So that's it. I'm not writing the whole dynamics. We could go on and solve this numerically and so on. But at the end of the day, the dynamics is such that the population will go to a fixed point, which is the stable coexistence between the resource and the consumer. I didn't analyze the stability of these fixed points, so I want you to believe me that this is a fixed point. It's the only fixed point in the system. So it's a global attractor, and at the end of the day, this simple consumer resource dynamics takes you to an equilibrium between resources and consumers. And obviously, there's a condition for this to be true, is this S has to be bigger than R star. Okay. Yeah.
Okay, so I don't really understand how did you got to that last formula there?
Okay, let's do it.
Because from the previous one, it doesn't seem like...
So this is like this. So I already know that R at the equilibrium is R star, okay? So what I do is here is that n star, this is equal to 0, yes? Will be what? Will be A S minus R star divided by R gamma R star. Okay? If you want, you can substitute M R star for M over R. It's okay now? Wow.
Well, now it's okay.
If you want to be explicit, you can write this down.
Yeah, okay, now it's right, because that's not what was written before you erased it. Yeah. It was written in the denominator.
Maybe I made a mistake. Okay. Okay. So if you want, you can cancel this and so on. You can play with this. Okay. So anyhow, you have a stable coexistence point between those. Okay. And so there is a condition. We need that the population of the consumers has to be positive number. Therefore, S has to be R so what does it mean? If we open this thing here, okay, this term here, it's the same as A times S minus A times R. Okay? A times S is the influx. So S determines the influx. And A is the mortality rate of the resource. Okay? It's a negative term. Okay? So A times S is the influx. But turned out that S has to be large enough in order to sustain the population, otherwise the population is not viable because there are not enough resources. Okay? So that's the condition for the population to be in equilibrium with the resource. There's a minimum resource level that has to be attained, otherwise you cannot sustain the population with this resource. Okay? And again, here what we took is one consumer, one resource, and the resource is the only one for the consumer. Okay? Why? Because we want to do things which go to the very heart of the dynamics. I could put, for instance, a current capacity for the resource. Could I do this? Yeah. But this means there's another resource. I am already with two resources in this case. Okay? So this would be weird. Okay? So, okay. You could ask yourself, well, what happens if S is smaller than R star? Then obviously the only thing you can have is N equal to 0. Okay? Because N not equal to 0 is also a solution. Okay? We try to find a non-zero solution. Yeah, there's a question.
Morning. I can see how this works, the resource equations, with an abiotic resource.
Yeah.
Because A and S, it's an inflow.
Yeah.
Yeah. So if we think in water, it could be the water cycle, this.
Could what?
Could be the water cycle, this influx.
Now, in this case, there are no cycles actually. That's why I use this, because it's linear and there are no cycles, and it's, so you don't have to go on in thinking maybe there's a limit cycle and so on, like Rosenzweig-Mercator. So I'm trying to do this at the simplest way. You could put instead of A times S minus R, you can put a logistic growth also. Okay, it's allowed. Okay. Okay. But well, it is sometimes little bit more algebra only. Okay, the results won't change.
Okay, then this influx can be the amount that we're going to rain at the in an state.
And it can also be, you know, this kind of bioreactors. You can just regulate in the lab the influx of resources for some species that you are. For instance, as I told, this can be done with not only with bacteria and so on. You can do this, for instance, with mites. Mites consume pollen, and if you want, you can have your mites in a certain in a certain place, which is called usually an arena, and every day you go there and you put some pollen for them. Okay, so it's biotic. Pollen. It's you can manage the system in this case. Okay, so it's externally controlled, right?
Okay.
So anyhow, as I told you, we can do this, could do this with other things here also. Okay. I want to keep the calculations as simple as possible. So only if remark that if s is smaller than 0, then the only fixed point is n equal to 0 here, because this one doesn't exist anymore. Then n is equal to 0 here, and n is equal to 0 here. Therefore, this means that the resource will be at level S. Okay, that's only dynamics of the resource without any consumer. Okay. Now comes, so this is just a consumer, one resource, and now we want something much more interesting, 2 consumers and 1 resource. So now we are talking inter-specific competition. And remember, what was our main equation to discuss the interspecific competition was the competitive Lotka-Volterra equation. Okay, everybody remembers or not? So that's just for I wrote it in this way. I don't remember, it was some alpha, I think. This was the system of equations that we analyzed, with all the graphical things and so on. But what was the take-home message? The take-home message was that the general tendency is to have competitive exclusion. One species goes to 0, the other goes to the carrying capacity, except if alpha and beta are small enough. We had a definition for small enough. Both have to be less than certain values connected to the carrying capacities. So, okay. So that, and our critique had been that alpha and beta are phenomenological parameters that cannot be measured before. Now, I don't want to recover these equations from consumer resource dynamics. It's much more tricky because you have to have 3 time scales, not only 2, because now I have 2 species and so on. And this will give you a longer calculation, which could be complicated. So we don't want to save Lotka-Volterra equation. We just want to see if I have 2 consumers and 1 resource, what will happen at the end of the day of this dynamics. Okay? So, okay, this was just for kind of reminder. Oh, so I will erase this because it has been already discussed pretty much. So now, as I know how to build a consumer resource model, which is this one, right? Now I have 2 resources. Which is R and 1. 2 resources now. 2 consumers minus M1, okay, R1, and M1. Okay? This is the consumption of the resource by competitor, by consumer 1. Consumer 2 has the same kind of equations. And the resource will have the same structure here minus, then I will say I have R1 times gamma 1 times N1 times R minus R2 gamma 2 N2 times R. Okay, so yeah. That's mechanistic, yeah. Because I'm not making any assumption like directly on the populations, because this is like predation, consumer. It can be measured independent of the population thing. You can do it with individuals, you can do it in observations, you can in principle determine, for instance, R and gamma. Okay? So it's there's a point of if you're talking animals, and that can be difficult and so on. It's not, I'm not claiming that for every species it is easy. Okay, but there are many research many consumer resources in the world, and some of them you can look at easily to see how is this kind of attack rate of the consumer on the resource. Okay, and this is what's called mechanistic competition theory. Also, sometimes it's called like that, and has been developed by mainly by Tillman in order to overcome the conceptual difficulties with the Lotka-Volterra competitive equations. So now I want to go for the fixed points. So this one gives me R star. Okay? It's equal to M1 over R1. Now this one gives me also R star. And it's equal to M2 over R2. Problem. No reason for both of them to be the same. I have two equations for one variable, R. It's overdetermined. So let's call this R1, this is R2. And what does it mean? There's no solution for R, okay? In this case. Except if instead of this I had taken, for instance, N1 equal to 0. Then I go back to this one, which is just the same as here, or vice versa. N2 equal to 0, then this is just what was there. Okay? So there are equilibrium points, which is equilibrium points are have always one of the consumers excluded. No way of having weak competition. Competitive exclusion is complete in this model. There's no way that two species feeding exclusively on one same resource to coexist. Okay, that's the message. Okay, and just for you to see this came very simply from the fact that these two equations do not have a solution. I mean, this equation determines R, and this also determines R because I'm cancelling N2 and N1. So I have two equations for one variable. This, in several exceptional cases, has no solution. Therefore, I need either N1 or N2 equal to 0. Okay? And this is independent of the dynamics I'm assuming for the resource. Okay? So maybe you were bothered as an abiotic managed thing, but you see that would happen exactly the same thing if I put a logistic here or whatever. It's super complicated the term. Even I could put many things here. Okay? So, but this I didn't even need this equation. Okay? Because I came to a contradiction with two of them. Okay? So this is valid for for much more general resource dynamics. Okay. Where's the mic on? There's only one mic today. The good one, yeah.
Sorry, it's going a bit too fast. Can you explain me again why R having two different explanations means one of them needs to be 0?
So how can I have this part equal to 0? Or in this part equal to 0?
And being equal to 0.
So I can have, this can have two situations. You could have n1 equal to 0, okay? Or you get the equation. This equation determines R star equal to m over R. The same thing can happen here. I could also have n2 equal to 0, okay? So I need both equations to be 0, both right sides to be 0. So if I want to look for the possibility of coexistence, then n1 and n2 have to be different from 0. Yes? But here, these equations give you a value for the equilibrium value of the resource. And this one also. And they are not the same. Therefore, there's a contradiction. So what was my hypothesis? That n1 and n2 were not 0. So one way of having this guy equal to 0 and this guy equal to 0 is just say n1 doesn't exist, it's 0. Then this one is 0 because n1 here and n1 here. And then you keep this equation, which gives you the resource level of equilibrium, and this is exactly the same as we had before, just one consumer. No? So let us solve the equations. Okay, this equation can give you n1 is equal to 0 and no determination of R. Right? Or another way is R, which I will call R star, that's the solution here, is equal to m1 over R1. Okay? Here. Okay, because this is nothing more than m1. Okay? So either this is 0 or either this one is 0. And this one to be 0 has to have this value for R. So this equation determines the equilibrium value for R, which I will, and the same thing will happen for this equation. Okay? Which is just changing 1 per 2. Okay, so this is being n2 R2 has two solutions, n2 equal to 0 or R star equal to n2 over R2. Okay, so now, question, can I have the population n1 and the population n2 different from 0 in equilibrium? If they are different from 0, then I'm not taking this solution here. Okay? I'm taking the solution, I'm taking the rest of this to be 0. So this is R star equal to m1 over R1, and this gives you R star. These are two different values. No reason for n2 over R2 to be equal to m1 over R1. So I obtain two. Therefore, which one? It's overdetermined. Okay?
What if they are equal?
What?
What if n1?
This is non-generic. Non-generic means that something happens if exactly, with all maximum infinite precision, two things are equal. And that never happens in nature. So non-generic case. Okay? They can be approximately, but approximately is not enough. Okay? So sometimes species that are pretty much similar, the same resource, that could be the same order of magnitude, but being exactly the same is something which is not generic. It's something that will happen never, actually. Okay? Because you would have infinite precision for both. Okay? So, therefore, I cannot have, in order to overcome this contradiction, I can take either n1 or n2 to be 0. If I take n1 to be 0, then r is equal to n2 over r2, which takes us back to one consumer, one resource, which was discussed before. Equilibrium, and so on. Okay? So, therefore, I don't have a fixed point with n1 and n2 different from 0. Therefore, one of them has to be 0, and one of them being 0 means that the one that is 0 has been excluded. Okay? Now, the point is, okay, we will have competitive exclusion, but which one exclude? What are the conditions for n1 to exclude n2, or vice versa? Which one wins? Okay? Which one will win the competition? Okay? So, just to make an interpretation for our, now I call this R1. Okay, may I go back to this one, just with the results instead of the calculation, so to save a space for the discussion. So, just to have an interpretation of these constants R1 and R2. So, R1 star, which is the equilibrium, the equilibrium level for the resource when only n1 is present. Okay? And R2 star is the equilibrium of the resource, equilibrium value of the resource, when only n2 is present. Okay? So, for instance, you could do something like that. You could do an experiment with two species with one resource. Now, first, you grow one species with a resource, and then separately the other species with the resource. In this case, you will have one growing here, here with a certain growth rate and so on, and will go into equilibrium, and the resource will be at equilibrium at, say, R1, and the other one will be at equilibrium at R2. The question is now, I mix it and let it eat. Question, which one will win? Okay, one has to win, because otherwise I don't have solutions, everything goes away. Okay? So, okay, so this analysis is something that we have to do. This is called invisibility analysis. Okay? So let us suppose that n1 okay, let R be R1 star, and therefore dn1 dt is equal to 0, And N1 will have an equilibrium population, which we now could go back here to find the equilibrium populations. This would be N1, okay? In this case, because I'm considering, let's have a situation where I want to have the population 1. And now I want to introduce the population of the species 2. So this would be like, I've grown this one, and then I have the population 1 at equilibrium with the resources, and I come and I put some competitors from N2. Okay? So the equation for the N2 will be this one, which is L1 star minus M2 over N2. Okay? So if I want this, now I want to know if when is this positive or when it's negative. Okay? So if this is positive, means that the population N1, which was the resident, when N2 arrives, and N2 will grow. We know at the end of the day that there can be only one population. Okay? So if N2 grows, means that N2 is able to invade, and therefore will go to carrying capacity and exclude N1. So the condition for that will be that, okay, this, if you want, you can write this way. The condition for that is that R1 star is bigger than M2 over R2, but which happens to be R2 star. Okay. Therefore, the condition, if this is fulfilled, we know that in this case, let me state this simply. Okay, if this, then N2 invades, which means that if the contrary is true, if R1 star smaller than R2 star, then N1 is not invaded, and N1 goes to carrying capacity, excludes N2. Okay? Yeah.
Good morning. So what does R1 or R2 means again?
Equilibrium populations of the resource when only one of the resources, one of the consumers is present.
Okay.
So say I don't have the N2, okay? I had just one end resource. Then R would be equal to this, and N would be something which comes from this equation. And therefore, this is the equilibrium population when only N1 exists.
Okay. So when we say that for N1 to exclude N2, the R1 needs to be smaller than R2, can we interpret that as like N1 is more efficient than N2 when using that resource?
Let's rephrase this. Okay, I'm coming to this point with the interpretation in a moment.
Okay.
Just let me just finish that. We obviously could do this, supposing that R is equal to R2 star, okay? And and to repeat the calculations and just changing 1 per 2. Therefore, the first thing was if R1 star minus R2 then N1 excludes N2 in the sense that N2 cannot invade. Okay? And if R1 star is bigger than this one, which should be the calculation made just changing every. I have this situations here. Now just change 1 per 2 and 2 per 1. You get exactly the same procedure. N2 excludes N1. Now, first just a small alert. This should be supplemented with the stability analysis for global attractors of the system. If I had introduced Holding type 2 things and all the Rosenzweig-McArthur stories and so on, I could have what's called not an equilibrium between consumer and resource, but you have a dynamic coexistence of changing population through cycles, which is rarely the case, but could happen if I had Holding type 2 with all the Rosenzweig-McArthur stories. And that's one reason to use this simpler thing, which is avoids to discuss the possibility of cycles. So, this one. R1 is the level of the resource, which is in equilibrium when only N1 is there. And then R2 is the equilibrium, the resource with the population N2 when N1 is not there, only population 2 is there. What does it mean? That R1 is able to be in equilibrium with the resource at a lower level of resources than population 2. Okay? Because population 2 will be in equilibrium with the resource when R2 star, and the resource has the level R2 star. Now, this means the equilibrium population of N1 is such that the resource will be at level R1, which is smaller than R2. Therefore, this is not exactly, it could be translated into, coming back to your question, somehow an efficiency, but well, we didn't actually introduce exactly this concept, but what we find is that the equilibrium that the condition for equilibrium is that the competitor that is able to be in equilibrium with the resource at the lowest level, at the lower level, will be the one that will win the competition. Okay. So, is this reasonable? It's reasonable. Okay, it's like you could do an experiment where you grow population 1 with the resource, and grow population 2 with the resource. This one will get to a certain resource level in the equilibrium. This one will get to another. Then you look at the value of this one and the value of this one. The one which is smaller predicts that if I put them to compete, the one that has a smaller R star will be the winner of the competition, which is a prediction. Now, you see, this is now a mechanistic description of competition, because I can do an experiment on population 1 and an experiment on population 2. I don't have anything like the force of competition effects like in the Lotka-Voltaire. I don't have anything like this. I can grow one of them separated from the other one, and if I mix, this theory now has predictions about the pattern of exclusions. It's not like the competition Lotka-Volterra theory, which had no predictions to give, because it depended on alpha and beta, but alpha and beta could not be known beforehand. So in this case, you have a prediction for the competition outcome. Okay? No possibility of coexistence of two consumers with only one resource. Now, yeah.
And if R1, R2 are equal?
It's non-generic. This will happen only when this would be exactly having such equalities. Is something that never happens, because when you say equal, this is mathematically equal. This is infinite precision equal. Okay? So, never happens. Okay? I mean, you could think of exactly, no, that never happens, because when we write this kind of, we can have inequalities, but we can't have this equality, okay? Because it's a mathematical condition of real being equal. If they are different, there will be one which is a little bit bigger than the other one, and then poof. We didn't discuss here how long it takes for a competitive exclusion. Okay, that's something we didn't. So first, how long does it take may depend on initial conditions. Okay? But besides, if they are very close, R star 1 and R star 2 are very close, maybe the transient can be long. Okay? But at the end, there should be an exclusion. Okay? So you could argue that when you look in this kind of systems, if their competition abilities, their consumer ability are very similar, maybe the dynamics is slow, and then you could see what happened that has all the appearance of being in equilibrium, but it's not. Actually, it's just changing slowly. Okay, so this is important to remember. So sometimes we can explain coexistence, thinking that they coexist, but which is not actual coexistence. It's just slow dynamics leading to extinction of one of them. Okay? Yeah.
I'm sorry, I just didn't follow where we got the inequality from. R1 star is bigger than M2, R2.
This comes from the same calculation, this same calculation, where I change, I put a 2 here, I put a 2 here, I put a 2, 1 here, 1 here, 1 here, and I change all of them, and then that's it.
I mean the one following from dn2 over dt bigger than 0. I didn't follow this step.
Bigger than 0 or smaller, I mean, the same way, exactly the same calculation.
Yeah, I didn't follow the step, the arrow.
What? Here?
This last step, you went from the derivative is bigger than 0 to R1 star is bigger than something. I didn't follow this part.
This being bigger than 0 needs this to be positive. Therefore, R1 has to be bigger than M2, over R2, which happened to be the definition of our R2 star. Okay. And the second one is just repeating this changing. When you have 1, you put a 2. When you have a 2, you put a 1. And Okay. So, one resource, two competitors, no way. What happens if you have two resources? 4 equations. Okay? So, how would we write down these equations? Okay, let's go put this here. Oops. If I have 2 resources, I will have 4 equations. But don't panic, we won't solve 4 equations, okay? I won't discuss the full dynamics here, because this would be complicated and so on. But I want just to see what happens, that it's different if I take consumer resource dynamics in this way. I took here 1 resource and 2 consumers. Now 2 consumers, 2 resources. So I would have this one. Okay. You would have a some R1. I will write this R11, which is the intake of resource 1 by consumer 1. It's just a way to, it's still just a parameter, plus R12, which is the intake of consumer 2, of resource 2, minus some mortality times N1. Okay? Now, I will write this one, which will give you R21, resource 1 being consumed by consumer 2 plus R22, resource 2 and 2. Here this was wrong. R2 and 1. Minus some mortality 4 and 2. Now, you still have 2 more equations, but I don't want to write them down now. I just want to see if, now, what happened when we try to do this calculation with, compare this equation for this equation. Okay. Here we had only 1 resource, and we had 2 equations here. And therefore this is overdetermined. It cannot be a solution. We would need this equality, which is not an equality. But now I have resource 1 and resource 2. Therefore, writing this equal to 0, now you say dn1 dt equal to 0 will give you R11 R1 star plus R12 R2 star minus M1 equal to 0. And here you have R12 R1 star plus R22 R2 star minus M2 equal to 0. R1 and R2, this is a linear system, 2 linear equations for 2 unknowns, R1 star and R1 star 1 and R2 and star 2. There's no contradiction anymore. Okay? I can have, we don't want to calculate R1 and R2. I mean, it's just algebra. It's just algebra. And there's no contradiction. Therefore, what happened here, which took us to the conclusion that there has to be some, always have to be competitive exclusion, is not anymore true. now you can have coexistence. Okay? Now, the difficult thing, and that's not part of the course, would be you can have coexistence, but do you actually have always or not? That's a better question, and that would take a whole chapter of a book to discuss. Of course, it's too much for us. Okay? But you can have coexistence of two consumers on two resources. Okay? That's okay. Yeah. Now, you can also have competitive exclusion. It will depend on the relations between all these parameters, which will be much more complicated than the discussion that we have done before. Okay? You can think maybe one of the consumers is more efficient on both resources. Then you expect competitive exclusion. Okay? But maybe if one is better on one and the other better on the other resources, maybe this takes you to almost to partition the niche and create a situation where you can have coexistence. Okay? So many possibilities actually. Okay? Don't want to discuss this, but this is a whole course about coexistence through consumer resource dynamics. Okay? And therefore, no. Yeah.
Oh, so in that second condition there, you start with R12, isn't it R21?
It's R21, yeah. Yeah, okay. So you have 4 constants, 6 constants, 2 unknowns, right? So it follows by the same method that if I have 3 consumers and only 2 resources, I would have again one equation more. I would have 2 unknowns for 3 equations which don't have solution, except if one n1 and 2 or n3 in the case would be 0. Okay, so the maximum number of consumers coexisting on n, say we have n resources. So the maximum number of consumers that coexist on n resources is n. Okay, because then you don't have the contradiction. Okay, if I had something like n3 here, but not R3, then I would get a new equation here. Okay, just putting 3's and so on. And then what I get? I get contradiction because I have only I have 3 equations for 2 unknowns. Okay, and then that's a mess. Okay, so so the main result of this discussion is that the number of consumers that can coexist on the on n resources, the maximum number is n. Okay? That's the thing. Okay? So this is a better theory for competition than Lotka-Volterra. But Lotka-Volterra actually captures some of this, but it's phenomenological and it was not clear what coexistence in the Lotka-Volterra system meant. It was weak competition, but what is weak competition? It was tautological. Weak competition is when they coexist. And when do they coexist? When the competition is weak, so tautology. Right? So now, not. And now we have something which is different. Okay? Now we have that weak competition means there's more than one resource. And then you can have coexistence of 2. Okay? So this is what we would call weak competition. We can now rephrase what we had. We can now understand what we had with the Lotka-Volterra competition model by resorting to this here and saying, okay, the coexistence that we found in the Lotka-Volterra competition model meant that there was more than one resource. Okay? That is an explanation for. So you don't have to throw away Lotka-Volterra competition model, but now you have at least some more mechanistic interpretation of what is a strong and weak competition. And this gives you here theoretical basis to discuss this concept. Okay? So then obviously then this takes you always to the famous discussions that we already mentioned, which were why are there so many species, or we could go back to also to Hutchinson's discussion of the paradox of the plankton. So plankton, not zooplankton, phytoplankton are basal species. And they have abiotic resources only, so they are at the very base. And well, zooplankton is different, but there are so many of them. So, but the abiotic species are how many? 10. Why are there so many species? Okay. And then this goes back to long discussions about coexistence mechanisms. Okay? Okay. And this obviously has to do with refugia, actually we are not seeing the coexistence, we are just seeing the transient. There could be several other interactions that are, maybe you have promotion of coexistence due to, say, another species. So you have two consumers, one resource, maybe there's something else happening, but maybe there's another species that predates the consumers, a top predator. So then you can think, okay, is one resource and two consumers gives you always competitive exclusion, but now if the top predator comes and predates has a stronger effect on the species that would win the competitions, then they could think of an equilibrium. So this kind of predation, this would be it's usually put like this diagram. These are sources for, say, A, top, consumer 1, consumer 2, resource. It's called a diamond diagram. Well, that's a community called community modulus. And for instance, here you could think of mechanisms where the presence of this top predator avoids the exclusion of one of the species because the predator predates preferably, or it has a larger effect on the species that would win the competition. Right? So this is gives rise to looking for what makes species coexist. And this is something which has been very fundamental in in ecological theory. Okay? Now, just to make a less discussion about this, let us go back to two consumers, one resource, but in a modified way. Do I still have them here? That's my equation. That's the one I want. Okay? Now let us think that maybe say species 2 has a carrying capacity. Right? So that's, I'm a bit messing up this nice discussion about mechanistic models because carrying capacity is not mechanistic anymore. Okay? But does it mean that, say, this species has, because here it does not have an explicit carrying capacity. Okay? It will go to a certain level of equilibrium, and if you want to call this equilibrium carrying capacity, that's okay. But here, let's say it has a carrying capacity. What does it mean? What was the carrying capacity describing? I didn't understand.
In case we're saying that one of the consumers has a carrier capacity, right?
Yes.
So this species will have a population limit, and probably the other one will surpass it.
No. So I just want to know the meaning of having a carrying capacity here. So the meaning, what that is, the carrying capacity accounts for what? Interspecific competition. Okay. Yeah. Okay. Interspecific competition. But now we are already describing the competition here. So why would I put a carrying capacity? Well, maybe there is interspecific competition in N2 for another resource, not the one that we are describing. Okay? So maybe there is a new limiting factor for N2. Therefore, implicitly, N2 has two resources. And two resources and two consumers could, in principle, coexist. So let's see if this actually works out, because we showed that the coexistence was possible when we had two resources and two consumers. Now, I don't want to model the two resources. I have one resource, that is this one, which is the shared resource. And then I will say, now I have a new one, okay, that restricts the growth of one of the species. Could be of both of the species, two carrying capacities. But let's make it simple, say only the one species has a carrying capacity. Okay? So what I will get here is, if I want to put a carrying capacity, just to remember, the carrying capacity always came with this term. Okay? Therefore, well, here, a carrying capacity term is something which should be minus r times n squared over k. Right? So I will put this r, let's put r2, n squared 2 over k. Okay. And now I want to put this equal to 0 and equal to 0 and see if I can have coexistence, if I can have no contradiction as I had before. So this implies that r star is m1 over r1. Okay? And this one would be r star will give you, no, okay, let me just do the calculations. And this one gives you r2 r minus m2 minus r2 N2 over K equal to 0. Now, no contradiction. I have R star. Let's put a star here. Put a star here. No contradiction. N2 is equal to K times R2 R star minus M2, all of this divided by R2. This equation, no contradiction. Because when I didn't have this was an overdetermined system. That's not anymore. Okay, I can now solve for N2. But obviously, now, if you want, we call this R1 star, and remember that we call this R2 star. Okay? And now you can figure out what should happen. If R1 star is smaller than R2 star, this would be negative. Problem. Therefore, N2 has to go to 0. Okay? In order to make this side here equal to 0. Remember, this was the condition for species 1 to exclude species 2, and continue to be valid. But now, if R1 is bigger than R2, then this can be non-zero. It's positive. This one is also okay. And you have a third equation which should determine the level of N1. Possible coexistence. There's no contradiction in the equations. Okay? So there are solutions which gives you R different from 0 and N2 different from 0 if this is positive. And then you can calculate the level for N1. Okay, I don't want to go over it. It's a little bit. Okay. So that's interesting that even not modeling 2 resources and 2 consumers, just putting 2 consumers with a resource, with a consumer having a carrying capacity modifies completely the story, because now I can have coexistence, because implicitly by introducing a carrying capacity for the species which I call 2, I'm assuming that there's some other limiting factor, and this limiting factor means there's some nutrient that regulates this population from bottom up, which means that there should be another resource. And having more resources, coexistence is possible. Not necessarily exists, because you see, could also lead to the elimination of one of them, but it is possible. Okay? So it's nice, and it makes a coherent view of the relation between number of resources and number of possible consumers that can be in equilibrium with the resources. Right? So this takes us back to the competitive exclusion principle. 2 species cannot consume if they coexist if they have if they feed only on one resource and the resource is shared, right? So they cannot coexist. This is explained. So let's say the competitive exclusion principle of Gauss gets redeemed here, in the sense that strictly speaking, if you have only one resource and two consumers, and the consumers depend only on that resource, then you have competitive exponential. Okay? So, and this opens up to the whole discussion about why species coexist.
Sorry, I didn't really understand how, from the second chain, how did the first equation become the N2 equal K R1 minus R2? How did that happen?
Let's do it here. I have this here, okay, R2 times R star, but this R star is this one, yes? Okay. Minus N2 minus R2 N2 star over K is equal to 0. So now I can multiply everything by K and divide by R2. So okay, K R1 star minus K N2 divided by R2 minus N2 star is equal to 0. Yeah? I multiplied everything by K and divided by R2. This is like this. Okay? So N2 here star. If this just you have to put here, it's equal to K R1 star minus K. But N2 over R2, what we had defined it as R2 star. Okay? This K R1 star minus R2 star.
So if we are assuming R1 star in this equation, that means we are working with the same scenario as before, N2 invading N1?
So I'm not doing the whole invasion analysis here, but it's an implicit. But what I'm saying, okay, we had the concept of R1 and R2 that still can be, if I have only the shared resources and I grow them separately, they will go to a certain equilibrium, which are and the resource will be R1 star or R2 star, depending on the species. So then here we are assuming that N1 is not 0, okay? So it's not 0, that means that the resource in equilibrium has to have this value, okay? Which happens to be R1 star, okay? And then I substitute this here, and I get this here through this calculation, which says that N2 star can be different from 0, provided R1 star is bigger than R2 star.
Okay, but why putting R1 star in the equation of N2? That's what I'm not understanding right now in this situation.
I don't understand.
Yeah, in this situation specifically. In the previous one I understood, not in this one.
So what's the definition of what we call R star 1 and R star 2? It's when I grow one species with only a certain resource. This will grow and go to equilibrium value. If I call this species 1, the equilibrium value of the resource with species 1 is called R1 star. And it's given by this. Now, if I grow R2 star, species 2 will be in equilibrium with species 1, with resource. And the resource level will be R2 star. Okay? I'm growing it only on that resource. Now, I'm saying, if I now make them compete for the resource, but I introduce a second resource which provides a carrying capacity for N2. Then I get these calculations, but still had the definition R2 star was M2 over R2. Okay? Yes? So this first one gets R1 star, and then when you wrap this here, okay, this says already that the resource has to have this value at the equilibrium. Okay? So then I put the resource here because it's already has been determined. Okay? The resource level.
Oh, so let me see if I understood. Because we already assumed as n1 different from 0, and therefore this value for R1,
yeah.
we will put this in the second equation because it's the situation at hand.
Yeah. I'm taking this one n1 different from 0, and I want to know if I can have n2 different from 0, which before we couldn't. Okay, before we had a contradiction. Using these two equations, we had a contradiction. Okay, so therefore that either n1 or n2 had to be 0, and then we showed, depending on the R stars, which one would be 0. Okay. Now I'm just writing one more term. I'm saying that there is a carrying capacity for the n2. Okay, and then, well, this equation remains valid. So R star, which I call 1 because we had discussed this before as being R1 star. I go here, and I can solve this equation. If this were not here, okay, this would be an equation for R1 again, and which would be a contradiction. But now it's not a contradiction because now this equation has become an equation for n2 in terms of R1. Therefore, you can get, at the end, you get this. And n2 can be different from 0 and positive if this guy is positive. Okay? So still, if L1 can coexist with a resource at a lower resource level than species 2, then still this is negative, then N2 has to be 0. But otherwise, you can have a coexistence net. So introducing carrying capacities is the same, has a kind of same result, or qualitatively the same as having two resources. Okay? You get again the possibility of coexistence. But in strictly speaking, with these kind of things, coexistence of n species needs n resources at least. And when you see coexistence which is different, there's something else happening. Okay? There are predators, there's mutualism, there's something else happening which could promote coexistence in a more complicated system. Okay? But consumer resource strictly gives you competitive exclusion when you have only n resources and competitors. Okay? So that's it. Come to 10:30. So, okay, so we have next class only, I think, on Friday. Yeah? Oh. Okay. Thank you. Okay.